Thank you. Someone said it sounds great. I hope it does.
All right. Hi, everybody. Again, thanks for tuning in today. So this week, our seminar speaker is Dr. Indujaa Ganesh, who's currently a postdoctoral researcher at the University of Alaska Fairbanks Geophysical Institute. Dr. Ganesh is a planetary scientist whose research focuses on studying volcanoes and the mechanics of explosive eruptions, in particular on Mars and Venus. And their research is quite interdisciplinary. They combine physical volcanology, radar, remote sensing, and so using different radar instruments, and then also doing field observations of terrestrial analogs. Dr. Ganesh earned a bachelor's degree in geoinformatics from Anna University, a master's in tech from the Indian Institute of Technology at Bombay, and then a master's in science and PhD in planetary sciences from the University of Arizona, where they just finished this past year. And as I mentioned, they just started a new postdoc in Alaska this past fall, where she was just mentioning it's been getting quite frosty already, even in October. And so thank you again for taking the time to talk with us. Take it away. Thank you again.
Yeah, thank you, Francis. And also thanks everyone for being very patient and staying with us through these tech troubles. And also, yeah, thank you all for taking the time out of your Fridays and attending this talk. Like Francis mentioned, I'm a postdoctoral fellow at the University of Alaska Fairbanks. My name's Indujaa. I just recently finished up my PhD at the University of Arizona. And all the work that I'm going to talk about today is research that was done as a part of my PhD. So all of this was stuff that was done while I was still at the University of Arizona in Tucson. So my goal for today's talk is to try and get people interested in and thinking about explosive volcanism or pyroclastic volcanism, specifically on Venus. So this talk is titled Forming Pyroclastic Deposits on Venus, Linking Radar Observations to Eruption Dynamics. And what I mean by that is, so we have all these spacecraft observations, so remote sensing observations of explosive volcanic deposits, pyroclastic deposits on Venus. And then on the other hand, we also have, thanks to a lot of previous people that have thought about this, have some hypotheses on how these deposits form. And what we're going to look at in this presentation are a couple of projects that have been done to try and bridge the two. So basically bridge what we know about remote sensing observations of these deposits to existing hypotheses of how these deposits form. Like I mentioned, this was done while I was still at the University of Arizona. So this couldn't have been possible without the help of a bunch of people, including my PhD advisor, Lynn, who is primarily a radar person, and then a co-advisor for one of the projects, Luke McGuire, who's a terrestrial geomorphologist, and then Triana, who is an undergraduate that worked in our lab. So the way I want to do this is start by briefly introducing Venus in the context of Earth, talk about some similarities and dissimilarities between the two planets and how that impacts volcanism. And then I'll talk a little bit about why studying volcanism is important, especially on Venus. And then we'll dive right into the two projects that make up the bulk of this talk. And I will wrap up with some results, how it connects to the bigger picture view, and also talk briefly about the upcoming missions to Venus and how these missions are going to help understand explosive volcanism and basic geology and geodynamics on Venus better. There we go. All right. So here we have two planets, Earth and Venus, that are very similar when it comes to size, very similar when it comes to bulk silicate composition, but that's kind of where the similarities today end. On Earth, we enjoy this cozy, one standard temperature pressure conditions in a nitrogen-rich atmosphere. Whereas things are very different on Venus today. So the atmosphere is very carbon dioxide rich, and it's about 92 bars of atmosphere at the surface. So if you were standing on the surface of Venus today, that in terms of pressure would be equivalent to standing about a kilometer under Earth's oceans. And then the surface temperature is about 460 degrees Celsius or 740 Kelvin. We haven't observed any magnetic field indicating an active dynamo within the planet. And we also don't have any large bodies or any bodies of water on the surface today. And an important distinction between the two planets that's formed the basis of several studies of Venus, and one that is very relevant to our talk today, is that there is no Earth-style plate tectonics on Venus today. And when I say Earth-style plate tectonics, I mean this full-fledged recycling of the outer shell of a planet. And we don't see that on Venus today. And the result of not having plate tectonics on Venus is how volcanism is distributed between these two planets. So if you look at Earth, which is the figure on top, we see that volcanoes indicated by these black triangles line up pretty neatly with the plate margins that are indicated by these purple lines and also by these sort of narrow or lighter gray lines. Now, if we compare this to Venus, which is the figure on the bottom here, there are two things I want to point out. Firstly, there's a lot of volcanism. There's volcanic features throughout the planet distributed everywhere. And then secondly, this distribution is pretty random. We don't see a specific pattern like we see on Earth. And if there is one, that's something we've yet to figure out. So even though we see all this volcanism on Venus, it's not the same type of volcanism. So on Earth, we have sort of two end-member types of volcanism. On one hand, we have effusive volcanism. This is kind of the quiet oozing out of coherent lava flows. And then on the other hand, we have volatile rich explosive volcanism. So this happens when the magma being erupted out is rich in things like water and carbon dioxide. And when this magma ascends, all these volatiles come out of the magma, they go into gas phase. These gas bubbles get bigger and eventually tear up the surrounding magma. And all this broken apart magma is then thrown out of the ground with lots of energy and velocity and momentum. And then we end up with these very typical tall ash columns, like we see on Earth. Now, studying both types of volcanism is really important on Venus, but studying explosive volcanism particularly is important for a couple of reasons. Number one, if you're thinking about secondary atmospheres of planets formed by volcanic degassing, effusive volcanism is capable of transporting volatile gases maybe a few hundreds of meters into the atmosphere, but we really need explosive eruptions with those tall ash columns like we saw in the previous slide to be able to carry volcanic gases well above the troposphere, tens of kilometers into the upper atmosphere. So for people interested in the atmosphere of Venus, trying to understand, was Venus's atmosphere always this way? Did it ever have atmospheric conditions in the past that could have been conducive for surface water and life to have evolved? And if that was the case, when did the atmospheric conditions change? So for answering questions like these, understanding the past volcanic history and especially how explosive volcanism fits into this is really important. And the second reason is we're thinking about the planet's interior. So like I mentioned, explosive volcanism is analogous with volatile-rich or water-rich magma. And through gravity and topography studies of Venus, we know that the upper mantle and the crust are anhydrous and dehydrated. So places where we see evidence of explosive volcanism likely indicate locations where this water-rich magma from the lower mantle has been brought up and exposed on the surface. So again, looking at these deposits then becomes important for thinking about how much volatiles Venus might have started with, how that was distributed, and how that has evolved over time. So what does volcanism and explosive volcanism on Venus look like? So firstly, I wanted to take a minute to point out that because the atmosphere of Venus is really thick and dense, we can't really image the surface using cameras from orbit. So the preferred way of imaging the surface from orbit above the atmosphere is through longer wavelength imaging, so through synthetic aperture radars. And this is often done by orbital missions like the Pioneer Venus mission or the Magellan mission. And till recently, one of the invaluable data sets that we've been using for this is also ground-based SAR observations from the Arecibo Observatory. So throughout this talk, I'm going to be showing images and using data sets from the SAR instrument that was aboard the Magellan mission, which is the very last NASA mission, I should say, to visit Venus in the early 90s. So when we look at what a Magellan SAR backscatter image looks like, that's shown on the right here. So a backscatter image is similar to looking at a camera image in the sense that places that are brighter indicate places where there's more reflection or scattering of the signal back to the instrument, and then places that appear darker are where we don't get a lot of scattered signal back at the instrument. And this is a typical image of what Venus' surface would look like. So we see these hundreds of kilometer long lava flows on the top here. We also see some smaller lava flows to the left here. And we see clusters of shield volcanoes at the bottom left here. So in short, we're seeing plenty and plenty of volcanic features, but predominantly all of this is effusive volcanism. And this is what most of the planet looks like. But there are a handful of places where we do see deposits that could likely be explosive in origin. And the figure on the left-hand side shows a couple of examples of these deposits. So this is Irnini Mons. This is a coronae on Venus. We don't need to get into what coronae are for this talk. For a brief definition, coronae are sort of these circular and quasi-circular features that are thought to be surface expressions of interaction between a mantle plume and the lithosphere. So what I want to point out is that on the outer flanks of this coronae to the north, we see these bright, sort of diffuse-looking deposits that I've marked out in these yellow dashed lines. And a lot of previous studies have suggested that deposits like these on Venus are pyroclastic in origin, and they are categorized this way and differentiated from lava flows for a couple of reasons. Firstly, if you look at lava flows, again, there's an example on the right-hand side. These are lava flows north of Tepe Mons. Now, within the lava flows, you can see sort of these differentiated flow units. For instance, all these arrows are pointing to a brighter flow unit. Just above that, you can see darker lava flow units. So we're able to make out different lava flow units within a single flow. Now, if you compare these to the proposed pyroclastics, we see that there are no such distinguishable flow units in the interior. It just has this sort of uniform fuzzy appearance going on. The second difference I want to point out is that the lava flows have these really well-defined sharp margins, once again pointed out by these white arrows here. And if we compare that to the proposed pyroclastic material, these units have sort of this feathery, fading out style margin and not a clear distinction between where this unit ends and the background planes are. A couple of other important things to note are that these deposits are really large. So both in terms of radial extent, so radially outwards from the circular structure, and also in terms of lateral extent, they extend for tens of kilometers. And they're often present at the summit of coronae and also shield volcanoes on Venus. And in some places, they are seen burying older lava flows, like pointed out on the upper left corner of this left-hand side image here. So this has led people to propose that these pyroclastic units likely indicate a later stage of more explosive eruptions on Venus that are fundamentally different from previous lava flow forming activity that they kind of bury. So how does one actually get explosive volcanism on Venus? We talked about the atmospheric pressure being really high. And what this does is it prevents volatiles like water and carbon dioxide from coming out of the magma and going into gas phase and eventually tearing apart this magma. So thanks to people that have already looked at this problem back in the 90s and also as late as 2015, we know that it is possible to get magma to break up on Venus as long as we can have enough volatiles. So the volatile weight percentages needed to achieve explosive volcanism on Venus are higher than what we would consider average volatile weight percentages on Earth, but they're not above the maximum volatile weight percentages that we find on Earth. Now, even with this high volatile weight percentage, when we do get explosive eruptions, not all of these volatiles can go into gas phase and break the magma apart. Only some of them do, and as a result, the resulting eruption will not be as energetic enough as it is on Earth. And when we don't have an energetic explosive eruption, it is hard to maintain a tall ash column for an extended period of time. And what then happens, as shown in the bottom right figure here, is that this ash column collapses, giving rise to these really hot flowing mixtures of fragmented magma and volcanic gases, and also sometimes entrained air that flow down the flanks of a volcano. These are called pyroclastic density currents, or PDCs, or pyroclastic flows. And these are examples of what these look like on Earth. On the top here is Tungurahua volcano. You can see a fresh PDC racing down the flanks. And right below it, you can see a fresh PDC deposit also on the flank of a volcano. And then the image at the bottom is from the 1991 Pinatubo eruption. What we're looking at is the flow front of a PDC. Now, given that it is hard to get energetic explosive eruptions on Venus, and that if there was an explosive eruption, it is likely to result in a PDC. All of these pyroclastic material that we are looking at on Venus have been proposed to have been emplaced from these PDCs, or pyroclastic density currents. So given the remote sensing observations of these PDCs, and given the hypothesis that they form, well, given the remote sensing observations of the pyroclastics, should I say, I'm sorry, and the hypothesis of how these pyroclastics form from PDCs, there are two primary questions we were interested in answering. So number one, how do PDCs actually emplace material on Venus? So what would the dynamics of a pyroclastic flow, not on Earth, but under Venus's ambient conditions look like? Can such a PDC be capable of transporting material across tens of kilometers like we see in the radar data sets? If yes, what kind of eruption conditions and vent conditions can produce such PDCs? And how would the topographic and ambient conditions on Venus impact this? So that's one set of questions which we will talk about in Project One. And then the second set of questions we had were, using the different radar observations that we have of these data sets, can we go beyond mapping them? Can we go beyond looking at geomorphology? And then can we answer questions about physical properties and physical structures of these deposits in a more quantitative manner? And this is the second set of project that we will be looking at today. We'll start with the first one, talking about PDC dynamics. This is very often done on Earth to understand pyroclastic density currents, especially from a hazard perspective. And the way it's done is very simple. People try and simulate how PDCs would travel over real topography. And in the case of, for simulating this, people often use things like digital elevation models, or DEMs. And here are a list of popular studies that look at this. And the modeling itself is very straightforward. One assumes that the pyroclastic density current is a two-component mixture. So you have a lot of broken up solids that are dispersed in a background fluid. This whole mass is then propelled forward by just gravity and topography, and frictional forces at the base of the flow, and then frictional forces between the solid particles in the flow, and any viscous drag that would arise within the fluid itself then act as resisting forces to the PDC. And on the right-hand side is an example of PDC simulation using two different models that get used for Earth, Titan 2D and wall flow. Now, as soon as we started implementing these Earth-specific models for Venus, we quickly ran into a couple of issues, which I will go over. The first one was more of a realization rather than an issue. And what we learned is that in order to form a deposit that is this big, so if we were to assume that these pyroclastic deposits were emplaced radially outwards from this summit structure, then to get a deposit that is laterally this extensive, we need more than a single eruption from a single source vent. So we need multiple eruptions from multiple sources that are distributed in space and or time in order to be able to form these really big deposits on Venus. So that was kind of our very first takeaway, or sort of pre-takeaway, when we started implementing these Earth models for Venus. The second thing, this is the main issue that we ran into. So if you think about where we get pyroclastic density currents and pyroclastic flow deposits on Earth, it is usually on the slopes of composite volcanoes with really steep slopes. And the steep slope can then accelerate the flow, make it flow faster, and travel for longer distances. Now, if we compare this with Venusian landscapes, where we're seeing these pyroclastic material on the flanks of Corona and shield volcanoes, which typically have topographic slopes of about 1 to 3 degrees, we don't get any topography-induced acceleration. So as a result, the resisting forces that I talked about quickly take over the flow slows down and ceases and does not travel very far and does not emplace material over tens of kilometers like we saw. So again, when we wanted to try and find an answer to this, we went back to the terrestrial literature, and it has been shown that a variety of mass flows on Earth, ranging from pyroclastic density currents to debris flows, are often very fluidized through the presence of excess pore pressure in the background fluid. So we wanted to try and incorporate this excess interstitial pore fluid pressure in our models as well. But unfortunately, what we found out was that the existing models like Titan 2D and wall flow are dry models, So when I say dry model, I mean that they do assume that there is pore pressure in the interstitial fluid, but then they also assume that this pore pressure is negligible and does not really affect the flow dynamics in any way. So we couldn't use these models anymore, and we ended up developing our own 2D pyroclastic flow model that is very similar in framework to say something like Titan 2D, but the big difference is that we no longer assume the pore pressure is negligible. So now that we have sort of this customized model, we could also add a little more additions to this. So the other addition we made was we tried and incorporated two different initiations of getting PDCs. So in the first case, in case A, on the left-hand side figure here, we assume that the ash column that forms instantaneously collapses and transfers all of its mass and volume and momentum to a PDC. And then the second type of initiation we looked at was instead of having a taller ash column, we kind of have like a boiling over style eruption where there is low fountaining going on, but it goes on for an extended period of time, thereby transferring a lot of mass into PDCs. So we took this model and then we tried this at 5 different locations. So 5 different locations that have pyroclastic deposits on Venus. And we picked these 5 locations because these were the only locations where high resolution topography data set was available for the planet. And then go over the results now. So I have a major takeaway and a minor takeaway to talk about. And this is the main result, and this is the major takeaway from this model. And what we find is that out of the 5 deposits that we looked at, the 3 smaller deposits, so not the 2 at Mnemons that we've been looking at, but the 3 other deposits that we looked at, they could have been formed by pyroclastic flows that result from non-energetic explosive eruptions. So even by having a column that is about 1 to 1.5 kilometers tall in the case of an instantaneous collapse, or by having just 50-meter high fountains that go on for maybe 5 to 6 minutes, it is still possible to form a deposit that is as extensive as what we see in the radar data set. And that's what's shown in the figure here. On the left-hand side, the gray line shows the mapped extent of the PDC deposit. The black lines indicate where we assumed the source vents for these flows would be. And then the black arrows indicate the flow direction of the modeled flows. And then the white shaded areas in the middle figure and also in the right-hand side figure show areas of the modeled extent of the proposed PDC deposit. So like I mentioned, we were able to successfully show that the 3 smaller deposits could have been formed from PDCs, provided the amount of material being erupted out is large enough to form such an extensive deposit, and the pyroclastic flow itself is fluid enough to carry all this material to longer distances. But again, this is only we were only able to do this for 3 out of the 5 deposits. The 2 really large deposits that we've looked at so far weren't things that we were able to successfully reproduce with this model, making us believe that one needs more energetic explosive eruptions than what we think could happen on Venus to be able to emplace these deposits. So this is sort of the main takeaway. And then there's sort of a smaller minor takeaway that I also wanted to talk about. And to do this, I want to look, so these are basically thickness, 1D thickness profiles along the deposit. So this AA prime, so the thickness along this AA prime is what we're going to look at in the next slide. So remember, A is closer to the vent and A prime is towards the terminus of the deposit. And what we find is that for a deposit that's emplaced by instantaneous collapse of a column, the deposit is thickest closer to the vent, and then it gradually thins towards the far end. And the overall thickness, if you look at the y-axis here, is generally smaller compared to the overall thickness for a deposit emplaced by a fountain collapse. You can see that by comparing the 2 y-axis limits here. And then the other distinction in terms of the deposit morphology is that unlike the deposits formed by instantaneous collapse that gradually thin towards the terminus, the deposits formed by fountaining kind of maintain this uniform thickness through most of the deposit extent. So these are properties, or these are differences in properties between deposits formed by two different styles that we can't currently make out with the data set that we have available. But these are differences that our models predict that in the future, when we do have better data set of Venus, can be tested out to try and better understand what the eruption conditions and properties of the eruption columns that form these deposits would have been. So that kind of wraps up the first project. I will take a minute here to re-emphasize the main result from this project, which was that it is possible to form some of the smaller PDC deposits that we are seeing on Venus without the need for really large, really energetic eruptions. So even with a kilometer-tall ash column or 50-meter-tall fountains, we can get PDCs that can emplace these large deposits that we see on Venus, provided two main conditions are satisfied. One, the volume eruption rates are high enough to erupt out enough material that can then be emplaced across this large extent. And two, the PDC that's transporting this material needs to be fluidized enough so that it can travel for long distances under Venus's sort of shallow topography conditions. So that is the end of project one. And then to remind people, project two was thinking more about the remote sensing observation. So we have all these different radar observations of Venus. How can we use this to say something quantitative about the deposits? So that's what we're going to look into for the rest of this talk. Okay, so when I say the different radar observations, what do I mean? So far in the talk, we've been looking at the Magellan SAR backscatter image. That's what's shown on the left-hand side panel here. So we looked at the Idnani Mons deposit, and we also looked at the model results through this P1 deposit at Pavlova Corona. And what we're seeing is all these proposed pyroclastic deposits that are indicated by these, or marked by these white dashed lines, appear bright in the radar backscatter image. So they have higher backscatter compared to the background material that they're emplaced on. So this is one of the radar measurements that Magellan mission made. Basically, you have an antenna that transmits a signal that's scattered back, and then you measure the reflected or the scattered signal back, and you have this backscatter image. So that's one set of measurements. And Magellan also made this other set of measurements called radiometry or radiothermal emission measurements, and that's shown on the two figures to the right-hand side here. And this is different from the scattering measurements in the sense that the instrument is no longer actively transmitting a signal and reflecting how much and measuring how much of that signal is reflected back. Instead, the instrument antenna gets turned off, and it is passively measuring how much energy is emitted from the surface at the same wavelength as the backscatter measurements are made. And by looking at these images, what we see is that unlike the backscatter, the emissivity values don't really stand out very much. They kind of have the mean emissivity values as the rest of Venus has, and in some cases maybe slightly has higher emissivity. And an important thing that I want to point out in these images is all of these pinkish yellowish areas, or sort of this, pinkish areas here and yellowish areas here that have anomalously low emissivity. So a puzzling effect that we've been seeing on Venus ever since Pioneer Venus time, so ever since the 80s, is that as we go up in altitude on Venus, the radiothermal emissivity drastically goes down, or in other words, the radar reflectivity goes up significantly. And there's been a few different theories to explain why this might be. On one hand, this is thought of as equivalent to a snow line on Venus. So as we go up higher than a certain altitude on Venus, all the metals can then condense on the surface, forming this metal snow or this metal frost. There are another set of theories that point to this being due to temperature-dependent ferroelectric behavior. In this talk, we're not going to go into what those different theories are or why they matter. Instead, we will collectively call places where we see this anomalous low emissivity behavior as high dielectric units or high dielectric medium. Now, previous people that have already looked at the radar signatures of these deposits have suggested that this high backscatter that we're seeing is primarily due to high roughness in the surface. So all of this is just surface roughness effects. So that's kind of where we wanted to begin as well. But before I start talking about that, let me point out another functionality of the Magellan datasets that we were able to take advantage of. So the Magellan mission basically mapped the planet in 3 different cycles. And SAR instrument, instead of looking straight below like a camera would, typically looks off to the side. So in cycle 1, as the radar was mapping the planet, it was looking off to its left. And then in cycle 2, when the radar was mapping the planet, it was looking off to its right. And then in cycle 3, the radar was again looking to its left, but now at a deeper incidence angle or a deeper look angle than for cycle 1. So this allowed, and in some places, including some of the deposits we looked at, there is coverage in multiple cycles. So we have both cycle 1 and cycle 3 coverage. And that's what's shown here for mini bonds. So this is cycle 1 SAR data set acquired at sort of a shallower incidence angle. And this is cycle 3 data set acquired at a sort of a deeper incidence angles. And what this allows us to do is then take these backscatter and emissivity measurements of these deposits and plot it as a function of incidence angle or look angle. So on this plot, the darker colors represent deposits that have been observed in both cycle 1 and cycle 3, so they have repeat coverage. And then the lighter data points, the gray colors, point to deposits that were, unfortunately for us, imaged only once. Now, once we have a plot like this where we can look at emissivity and backscatter as a function of incidence angle, we can start fitting scattering loss or scattering functions to it. So remember how a couple of slides ago, I pointed out that previous studies have already suggested that the backscatter and emissivity that we're seeing are primarily a function of surface roughness. So there are several existing radar scattering models that get used in earth science that basically try to understand what scattering from a rough surface would look like. So we took one such model, which was the improved integral equation method, as listed on the right-hand side here, and applied it to a subsurface scenario, which we assume has high roughness and some amount of dielectric constant. I will briefly talk about what that is in a second. And then we look at what the total backscatter and total emission from such a geologic unit would be. And the results are basically shown on the left-hand side here. In simplistic terms, what we're trying to do is we're taking these different data points at different incidence angle and trying to fit a multitude of curves to it, corresponding to different sets of roughness and different sets of dielectric constant. And what we find is that in addition to having moderate to high surface roughness, we also need a dielectric constant or relative permittivity or dielectric permittivity of about 5 to 7 to be able to match both the backscatter and the emissivity observations. So not only is high surface roughness enough to cause this high backscatter, moderate emissivity behavior, on top of this high surface roughness, we're also needing relatively high values of permittivity of 5 to 7. And the reason I say that this is relatively high is because the mean permittivity value for Venus's plains is thought to be between 4 to 5. Now, for dry materials, like on Mars or on Venus, where we don't have to worry about soil moisture, there are easy ways to relate this dielectric permittivity to a more relatable quantity of density. And when we use those relations to convert this permittivity to density, we find that the bulk density for such a geologic unit would be between 2,500 and 2,900 kilograms per cubic meter. So keep this in mind. We'll come back to this again in a couple of slides and talk about it. Okay, so radar waves typically don't just scatter off of the surface of a material. So depending on what the radar wavelength is and depending on what the properties of the geologic target are, one could also have radar waves that penetrate through into the subsurface and can get scattered back to the instrument by structures in the subsurface. So this can happen in 2 ways. So one, we could sort of have this continuous interface in the subsurface. For instance, if we had 2 lithologic units, say we had some kind of sort of a regolith type friable deposit that's sitting on top of a denser bedrock, then the contact between these 2 deposits would appear as a continuous interface to the radar. Or on the other hand, instead of having a continuous interface, we could also have broken up distributed scatterers. Pyroclastic density current deposits often have things like lithics or pumices. These are centimeter scale structures that are embedded throughout the deposit. And these different inclusions would also scatter radar signal back to the instrument. So we wanted to incorporate these two different deposit structures to our existing models. So in order to do that, we went back and used the I²EM, the improved integral equation method, to calculate what scattering from any of these continuous interfaces would be. And then we supplemented that with a radiative transfer approach to calculate backscattering from buried intrusions. This is not used in earth scientists a lot, but radiative transfer approach is something that atmospheric scientists use often to think about light scattering in the atmosphere. So a similar approach, but applied to scattering from rock intrusions within a geologic material. So quickly go over results from the two. First case we're going to look at is the subsurface scattering from a continuous interface. So what we find is that if we assume that most of the scattering is happening from a buried interface, then there's only a specific set of conditions which give rise to backscatter as well as emissivity that matches our observations. And these conditions involve, number one, having a pyroclastic deposit that's very thin. And by thin, I mean the same wavelength as the radar, which in this case would be about 13 centimeter. And the geologic unit that's buried beneath the bedrock will need to have high surface roughness. And then the bedrock will also need to have really high reflectivity or really high dielectric constant, very similar to some of these yellowish pink low emissivity areas that we saw close to these deposits in some of the locations. So what our model is showing that is that the only geologic scenario that if modeled as this two-layer structure would satisfy the radar backscatter and emissivity measurements is having a very thin layer of loose friable pyroclastic material that then covers up a bedrock that is made up of high dielectric substance. And then we also looked at the volume scattering case. So this is the distributed scattering from the subsurface case. And we quickly wrote this, and I will point out why. So when we look at the scattering curves and compare the volume scattering curve to what some of the previous scattering curves look like. So this is scattering from continuous interfaces, and this is scattering from distributed interfaces. And we find that scattering is largely independent of the incidence angle. So it doesn't matter what incidence angle you're looking at, we pretty much get the same amount of backscatter. And that is not what we're seeing in the data. We're seeing statistically different backscatter values for deposits that were observed at cycle 1 and cycle 3. So even though we tried this out, we quickly wrote this off as being a possibility for a possible explanation for what we're seeing in the radar data set. So what does all of this mean? So in short, we tried 3 different possible deposit properties and deposit subsurface structure to explain the radar signatures, the backscatter and the emissivity signature of these proposed pyroclastic deposits. We quickly wrote scenario 3 off. So this is the case where we assume that you have a thick pyroclastic deposit that's low in density, that's kind of loose and friable, and has a lot of distributed inclusions, like maybe wide spaces or rocks inside. And that did not match our observations. So that left us with 2 possibilities. The second one we talked about is where we have this really thin, loose pyroclastic material on top of a high dielectric bedrock. Now, we also don't favor this interpretation, mainly because the thickness that's predicted by the radar scattering models, which is only tenths of centimeters, is very different from the tenths of meter thickness that we're getting from looking at flow models, from the pyroclastic flow models that we looked at earlier in the talk. So mainly because of this, we also don't favor scenario 2. So that leaves us back with our very first subsurface structure that we theorized and went with. This is having a thick geologic unit that has a rough surface. But then the main difference between how previous studies have envisioned this deposit and how we're envisioning deposit is that having a rough surface alone is not enough to explain this high backscatter behavior and this moderate emissivity behavior we're seeing. In addition to high roughness, we also need a relatively high dielectric constant, which translates to relatively high density of about 2,500 to 2,900 kilograms per cubic meter. So this is typically higher than the density of a friable, loose, non-welded pyroclastic deposit that one would find on Earth. And the only way to explain this high value is if the pyroclastic deposit during emplacement was hot enough for all the particles within to fuse and weld together, forming this like welded high-grade thick deposit, similar to welded ignimbrites that we would see on Earth. And I quickly want to point out that this is not the first time anyone's talked about welded pyroclastic material on Earth. This was done by Head and Wilson as early as the 1980s, but they envisioned such a deposit very close to the source wind. And we are proposing that such deposits could also extend for several tens of kilometers away from the wind. Okay, so the main takeaway from the second study, which is on the right-hand side here, is that based on the radar backscatter and the emissivity signature of these deposits, it is quite likely that the pyroclastic deposits on Venus are very similar to welded pyroclastic flow deposits on Earth. And that's because we can't explain this high backscatter using surface roughness alone. So these two studies kind of looked at a few different aspects of explosive volcanism on Venus and tried to understand how this could go on, but we still have a lot of unanswered questions about volcanism on Venus. And I will try and highlight a couple of things that I think need to be prioritized and are very important and are things that I'm interested in. And we'll start with the one on top here. So going back and thinking about how we actually get explosive eruptions on Venus. So we talked about just having higher percentage of volatiles to get explosive eruptions on Venus, right? And this is based on studies as late as 2015. Now, even between 2015 and today, there's been significant advancement in terrestrial volcanology in thinking about how explosive basaltic eruptions work. So a lot of work, including Pranabendu Moitra's work, he's a researcher at the University of Arizona, has showed that having crystallization in basaltic magma promotes the breakup of magma. And that's not something we've thought about for Venus at all. And then another set of work that looked at explosive eruptions in the San Francisco volcanic fields, which are also primarily basaltic, showed that having magma supersaturated in carbon dioxide was also important in promoting explosivity. So these are new ideas that we're starting to develop about volcanism on Earth. And I think it's important to go and revisit volcanism, not just on Venus, but planetary volcanism in general, given these new and evolving ideas that we have about basaltic volcanoes on Earth. Another couple of important things that I want to point out here are understanding when these deposits formed. So we don't know the absolute ages of any unit on Venus. So trying to understand what the ages of these deposits would be, when they formed relative to other deposits, did they form when the atmospheric conditions were still with 92 bars of pressure, or did they form when the atmospheric conditions were slightly milder? That would also be important in understanding what kind of eruptions or how energetic explosive eruptions could be on Venus. And another important thing that we don't have yet for a lot of places on Venus is understanding what the composition of the magma that has been erupted out might be like. So do we have, as all of this primarily basaltic magma, can we have more evolved and intermediate compositions? And again, these are questions that we don't know the answers to because we don't have enough data about Venus. But thankfully, we have 3 different missions that are definitely flying to Venus in the next decade. There are 3 very different missions. There's the NASA Da Vinci mission that's going to fly first. This is an atmospheric descent probe that will kind of travel through the atmosphere and take measurements of the physical and the chemical properties of the atmosphere at different altitudes as it's descending. And as it gets closer to the surface, it's going to get 3D high-resolution images of the landing site where it's going to land. And then we have another NASA mission called Veritas, and then an ESA mission called Envision, both of which are orbital missions that will that are similar to what Magellan, that are similar to the Magellan mission, but also different in their own ways. And because I'm either formally or informally associated with these couple of missions, I know a little bit more about them. So I want to take a minute to talk about them. So both these images have synthetic aperture radar instruments on board. And these instruments will be invaluable in returning back high resolution images of the surface. So higher resolution than what we saw in this talk so far, higher resolution than Arecibo, higher resolution than Magellan. And these will also be the first time the planet's surface has been imaged in the past 40 years by the time the spacecrafts get there. So for thinking about the current rate of volcanism on Venus for a planet that's the same size as Earth, do we see the similar level of volcanic activity on Venus? Having this data set is going to be really important. And secondly, both of these spacecraft missions also have a near-infrared spectrometer on board. So using these spectrometers, we might be, for the first time, be able to see if all the rocks on Venus are basaltic in composition, or if we might also have more intermediate or felsic compositions. And then both of these instruments also will do gravity and topography measurements. Once again, in the absence of in situ landed measurements, landed geophysical measurements, gravity and topography provide the best way of constraining what the interiors of planets look like. So once again, we're trying to understand if there could be active volcanism, where that could be happening on, where that could be going on, if there are active plumes on Venus like we see on Earth. Having these data sets is going to be super duper helpful. With that, I will put my conclusion slide up on top. I'm happy to take any questions. If there are questions that we don't get around to today, people are also welcome to email me. I put my email down at the bottom. And with that, thanks everyone for bearing with me for the past 45 minutes or so.